X bar and R chart. You can also do that, insert a row and then type out what the objective is for today. Objective, X bar and R charts to understand process variation over time. Okay, so this example, by the way, could be anything. These numbers could represent anything. Let's say these numbers are specific, and suppose these are this is a pasta box that you get at Costco. This is a box of pasta, let's say, that you get at Costco, and these are how many ounces of pasta you want in that box. That's the requirement. So what's the requirement? Let's write it out here. Requirement from the process, 64 ounces of pasta in a box sold at, say, Costco. Now I'll qualify that 64 plus minus 1. Plus minus 1. And so you allow for some variation. Okay? And so we'll talk about different types of variation. But just at the outset, this is the requirement from the process. Now, what are you doing? Let's say you're the supplier who's supplying this pasta to Costco. And obviously, you don't want to check 100% of your output. You don't want to check 100% of your boxes because that would be counterproductive. That would take a long time. You can do better by sampling. Remember, we discussed the example of how in an election, you have 120 million voters. It's possible to just ask a few voters to get an idea of what the variation is like, to get some confidence. It's the same concept here. Instead of checking 100% of your output, what you're doing is, let's say you just check every hour, you take 4 boxes of pasta from the assembly line or from the packaging line, and then check how many ounces there are. You weigh it and you check how many ounces of pasta there is in that box. So these are your samples. So you do this for 10 hours. It works a 10-hour shift. Let's say the facility works a 10-hour shift, and every hour you go and collect 4 boxes. Okay? And these are how many ounces you have in each of those boxes the first hour, each of those boxes the second hour, each of those boxes the third hour, and so on. What we want to observe is how does this process change over time? Is this process, is this in control or not in control? In control or out of control? Because if it's out of control, you need to take corrective action. If it's in control, you don't need to take any corrective action. Everybody see? So this is kind of a predicate. This will help you decide whether you want to take action with respect to the quality of your process or not. Okay. First things is we want to define what's known as the sample size. This is very important because all the calculations are tied to this sample size. So what is the sample size? First off, look at this table. 10 hours, 4 boxes each hour. What's the total number of observations you have over those 10 hours? 40. Okay. And just to note, this is not the sample size. Okay, this is not the sample size. You're doing this every hour for 10 hours. Even that is not the sample size. Sample size is not the 10 hours over which you collect the data. The sample size is how many observations you collect in a relatively short period of time within that 1 hour. This is the sample size. So tell me what the sample size is. Is what? 4. That is the sample size. What's the logic here? Remember, what happens as you collect a bigger and bigger sample? Do you get more confidence or less confidence? You get more confidence as you increase the sample size. More confidence in this case to do what? To certify a process. If you collect more samples, if you increase your sample size, you'll be able to say with more certainty that this process is in control or out of control because there's always underlying randomness. You can always have an outlier in your data that can cause your control chart to go out of whack. But if you collect a large enough sample, when you take the average, it'll even things out. Everybody see? So confidence to do what? Confidence to give a certificate. Ultimately, what's the objective, as we said? We want to create these X bar and range charts to understand process variation and give a certificate hey, this process is in control versus this process is out of control. And the confidence you'll have in that statement, in that certificate, is actually much higher as you increase not much higher, it increases with the sample size. Okay, so that's the objective. And we're going to use these control chart factors. And at this point, it does become formulaic, which is why I want you to actually do this with me. Because if you don't do this once, you will not know how this works. Okay, this is formulaic. Remember your Z table from normal distribution? This is very similar to your Z table, only there are different parameters. A2, capital D3, capital D4, capital D2. If you're interested, you can pick up any quality control handbook. It'll have all that information. But doing that is beyond the scope of this class. All these are parameters based on the normal distribution. And these parameters, as you see, all depend on the sample size. Everybody see? That's why it's very important to get the sample size right. Now, to finish the point here, why is the sample size 4? Why is it not 10? Because you're taking 10 samples, right, of 4 observations each. Everybody see, you can also interpret it that way. You're collecting 10 samples of 4 boxes each. That's another way to look at this. But the sample size is not 10. Why? The sample size is the number of observations you collect in a relatively short period of time. Why do we think of it that way? Because we don't want the process to change a lot in that relatively short period of time. Okay, and so now you have a much better chance that the process is the same as it was if you collect it in a short period of time. That's your sample size. What is the sample mean? X bar. So X bar is the sample mean. So what's the sample mean? Can you help calculate? So once you have a sample, how many observations in the sample? 4 observations. What's the average of those? Can you help calculate? Do it. Take the average. Yeah? 64.63. Similarly, just drag and drop. This is the average. This is what we are plotting over time. In fact, you can draw your X bar chart. You can insert a chart. I'm going to delete it as soon as I insert it. But just to show you, you can actually draw this. You can actually chart it. This is what we want, this is what we want to do. But the problem is, this is not relative. This is not relative. This is not telling you anything. How can I know this process is in control or out of control? I need to know the limits. Is it exceeding some limits? Is it within limits? Then I can certify in control or out of control. And so really the challenge is, this is easy, right? Everybody see? Just plotting the averages, that's easy. What's the real deal is in calculating, the real effort is in calculating the limits on the plus side and the minus side. Okay, so let's do that. Let me put this aside for now. You don't need to delete it, we can add always. And so we want to calculate these limits. But first let's also calculate what's known as the range, or R. Range R. What's the range? The range is nothing but the difference between the maximum, the max value. Can you just do this without the formula? What's the maximum among these 4 observations? 65.70. And what's the minimum across these 4? 63.6. What's the difference between the two? 65.7 and 63.6 is 2.1. Everybody see? That's your range. That's telling you how much spread there is, how much random variation there is in the data. Okay, that's the right, the spread. And so this is going to be max minus min. That's 2.1. Similarly, go ahead, drag and drop, and tell me once you're done.
Answer the question for export sample.
In fact, I'm going to call this sample range as well. Sample range. because this is the range from within your sample. Okay. So, and what we want to do is, again, I'm going to draw a chart with just the range values. This is exactly what I want to plot, except I need to also understand relative to what. How do I know this is in control or out of control? These are the two charts, the X bar and the range values we're supposed to draw. By the way, it's not enough to just look at one. You have to look at both. Which means what? If you want to certify in control, both of these charts must be in control. If one of them is out of control, then your process is out of control. So if, for example, the sample average X bar chart is out of control, then you say, listen, systematically your average is changing in a way that's kind of beyond what you expect, and therefore that's an alert, and that should trigger some action. So to say out of control, you just need to look at, right? You just need to have one chart out of control. If you want to say in control, both of these charts must be in control. That's a harder check, harder test. Bar, or the X double bar, which is the grand mean, grand or process mean. Okay. This is my process mean. Let me actually do this, text. And what's my process mean, given my X bar values? How can you calculate that? As the average of the averages. That's why we call it X bar bar. Bar is over bar, and so bar means average. And so if you're taking twice the average, which means you're taking average of the average. You can do that, or you can also take the average of all these 40 observations. Doesn't matter, because every time our sample size is 4. It's consistent. And so no matter what you do it, some of you can try it one way, some of you another way, you'll see that you'll get the same answer. Take the average of all these average X bar values, and what do you get? 64.15, is that what you get? So, and so now 64.15, so I'm going to call this the center line for the X bar chart. Center line X bar, I'm going to plot it. That's why I want to enter these numbers. And so here I'm going to go get the X bar. I'm going to put a dollar sign on the column because I'm going to drag to the right, and then I'm going to plot it. Everybody okay? Now, how do you add it? You can just right click on the graph, select data, and add your center line. And the values are just add that line to your graph. Next, okay, so we're going to calculate what's known as the upper control limit for the X bar chart and the lower control limit for the X bar chart. So first, let's calculate the process range, process average range, which is nothing but the average of the range values. Go ahead and calculate this, and then we'll be ready to calculate it. What's the average of all these sample range values? That's our R bar. We call this R bar. Okay. So everybody with me? Do you get 2.39 for average? Yes? Sorry? You get it? Kashayar, you get 2.39? And so now we're going to calculate the upper and lower limits based on this X double bar and the R bar values. So what's the upper control limit? It's going to be process mean plus A2, which comes from the sample size. Read off the A2 value. This table is fixed. It's like your Z table. It doesn't change for the normal distribution. Okay? The only thing is you see these numbers changing with the sample size. So go and read off the row from a sample size of 4. Remember our sample size is 4? That's what I've highlighted here. Go and pick off that number, which is 0.73, and multiply it by the R bar value. That's your upper control limit. That this is going to be my process mean or my grand mean minus A2 times R bar. Good. $M7 and then $M8. That should do the trick. 0.73. Where does that come from? That comes from B20. I guess you can say it's $B20. It doesn't matter, but it's $B20. Yeah. But if you're in doubt, put $2 signs. You can't go wrong. That's extra redundant protection for you in case you do end up making a mistake. But here you should get the same. Just $1 sign does the trick. Because what's the purpose of the dollar sign again? Notice as we are moving right, we're always sticking to the same column. When I say $B20, it's fixing the column value at B. And then as you're moving right, it keeps that column the same. Okay? And now, similarly, before we go ahead and complete the charts, let's actually go ahead and create these limits for the R chart as well, range chart as well, and then we'll draw. Okay? So what's the center line for the range chart is just your R bar value. Center line, R bar, and so that's just going to be your R bar value. Again, put a dollar sign. That should be good. Now, what's the upper control limit? It's going to be capital D4, which is this 2.28 multiplied by R bar. Here we'll put the dollar signs. Now we know why we want the dollar signs. So it's going to be capital D4. That's the control chart factor you're going to be looking at. Capital D4 corresponding to a sample size of 4 times your process average range, R bar. And what's your lower limit? It's going to be capital D3 times R bar. Again, as I said, this is formulaic. Why is this formulaic? Because this dates back to the 50s. That's when they first developed these control charts. In the 50s, you don't have computers. So just like the Z table, you had to read off a table and then use those values. These days, of course, you don't need this. But this is the traditional way of doing it, the quality manual kind of doing it, the way of doing it. So do you guys get the same numbers? 5.44 and 0. Let's drag it to the right. Now we're ready to draw the charts. Okay. So why don't you go ahead and add for the X bar chart, the first chart, that's plotting your X bar values, the sample average values. Also, we've already shown the X double bar, the center line. Go ahead and also show the upper limit and the lower limit for the X bar chart, what we calculated up here. So what I'm going to do is come down here and right click on this chart and say select data, and I'm going to add 2 new lines, one for the upper control limit with values, it's going to be the same value, and then one for the lower control limit. The name is plus minus something times R bar. What's happening to your R bar with more variation within the sample? The R bar is getting beefed up. It's getting bigger and bigger and bigger. And so that's, again, goes back to the critical point. Statistical process control only refers to consistency of your process, not to what the customers are asking. Customers could be asking for the moon, but you're still going to say your process is in control if it's consistent and not even meeting customer satisfaction. So it's only based on historical performance. Everybody okay? Good? All right. So that's the idea. And then similarly, let's go ahead and add these lines for the sample range chart. Here I have Here I have a title, and here we don't have. So go figure. Sometimes Excel and Mac is not kind of the best option dealing with. So here's the sample range chart, and our chart. And I'm going to add these. Right click, and then select data, and I'm going to add the center line. And then I'm going to add the upper limit. Then I'm going to add the lower limit. And you come down here, and so same deal. Everybody see? This is the upper limit, this is the lower limit, and this is your center line. Now, is this symmetric around the center line? The limits? In this case, are the limits symmetric? Because on the one side, do you see that D3 is 0? Everybody see D3 is 0? No matter your range value, if you don't have enough of a sample size, it's automatically zeroing it out. Why do you think that is? Why is the lower limit arbitrarily 0? No matter the range value, no matter the R bar, lower limit is automatically 0 up until this certain sample size. If you notice, sample size of 2, 3, 4, 5, 6 is 0, and then it starts to pick up. What's the purpose, you think? The idea is that can range be negative? Cannot be negative. And so remember what these limits are telling you. The limits are giving you some confidence. The closer the limits are together, the more confidence you have. How would you get that confidence? If your sample size is higher. That's when you get the confidence. Everybody see? And so what's happening to these limits? You take the difference. If you take the difference, notice the difference between D3 and D4. Let's calculate the difference, D3 versus D4, and right, D3, capital D3 versus D4. So notice the difference here is D4 minus D3, so if you see here, what's happening to this difference between D3 and D4 as you increase the sample size? It is getting closer and closer. And this is exactly what's going to happen. These limits are going to get closer and closer as your sample size increases. And conversely, the limits are going to get farther and farther apart as the sample size is smaller, which means you don't have enough confidence, except as it's getting further apart, you cannot have negative range. You cannot have range less than 0. Everybody see? That's why you arbitrarily cut it off at 0. Everybody okay with what we're saying? Because the range cannot be negative. That's why it's saying you don't have enough confidence on one side, but it can't be below 0, so you cut off at 0. That's why it's not necessarily symmetric. It will start to look symmetric beyond a certain point, but it's not symmetric. The range chart is not symmetric around the central or out of control. So let's look at the X bar chart first. In control, out of control? Visually, yes. But here's why you need rules, because my eyeball could be different from your eyeball. My eyeball could be telling good things. Remember the statistical saying? You can make the data say what you want. And so that's why you have rules. So what are some rules? I have those on the slides, by the way. Even if you have one single point above, this is the visual aspect. Even if you have one single point above or below, what point? The X bar values, the blue line. If it crosses the limits even once, ding, not in control. Okay, that's simple. Here's what's not simple. You're also looking for consecutive points above or below the center line. For example, if you have 5 points successively above the center line, that's not good. That's telling you there's a systematic shift on one side. Okay, everybody okay? Similarly, 5 points below, that's also bad. If you see 2 or more points successively hugging the line, that's called hugging the limits, which means again there's a danger you'll cross over. So 2 or more successive, ding. close to the limits. Like in this case, you don't see, you have a reasonable cap, okay? And also, 5 successive points increasing or 5 successive points decreasing, that's again bad. That's telling you there's a trend in one direction or the other. That's also bad. Remember, our objective here is not to have any systematic variation. This is just random variation, ups and downs random. I don't care. Systematic variation is bad. Random variation, I'm okay, because I'm not getting penalized for random variation. Because the random variation higher, my limits get more relaxed. I'm actually not so bad. I'm in good shape. So systematic variation is the purpose of statistical process control charts. Your purpose is to understand and flag systematic variation. Everybody good? These are some rules. So again, just to recap the rules, any single point above or below, ding. 5 points above consecutively or 5 points below consecutively, ding. And 2 or more successive points hugging the limits on either side, again, ding. And 5 or more successive points increasing or 5 or more successive points decreasing, again, ding. And the last one, this is the hardest, which is any systematic cyclical pattern. For example, every 5th point above and then all the remaining 4 points below. That's systematic. Which should tell you, for example, on the line something is happening, which means they're taking a break every 5 hours or 4 hours. And then once they come back from the break, they need some time to kind of refocus. That's systematic. That's something you can fix. And that's something you can flag. The challenge is it's hard to find out cyclicality. For example, think about this. Is this reasonably cyclical? Yes, it is. You have some points above and some points below. Some points above, some points below. And so your eyeball may see systematic or a pattern. My eyeball may not see a pattern. This is hard, and but nevertheless, it's one of the rules. If you see these systematic or cyclical patterns, that's again a flag. Everybody okay? These are the rules. The same rules apply to the R chart. Again, you have to check for 5 consecutive points. Do you have 5 consecutive points? 1, 2, actually this is not. This is 2.39, which is identical. So you can check. You can go for the third sample. What was your range value or bar? Sorry, range. 2.3 versus 2.39. So this was actually slightly lower. Everybody see? Oh, but we are talking about the second one, right? The second one is actually 2.4 is just higher. Everybody see? So you don't get 5 consecutive points below. 1, 2, 3, 4. In fact, there's only 4 here. Nothing to worry about. The 5th one is above. And do you see a trend? 1, 2, 3, 4. But really, increasing starts from here. 1, 2, and 3. Only 3 points successive that are increasing. Okay? Everybody see? Again, I don't see any reason here to say that this process is out of control. Do you see any cyclicality that I don't see? Anybody see a cyclicality here? Systematic cyclicality, ups and downs. You do see ups and downs, but it looks like it's random. Okay, as I said, that's always going to be the challenging part. You don't see any 2 points, successive points hugging the limits, so it looks okay. And so now, only if both charts check out okay, then you can say this process is in control. So now you say both charts pass all tests, hence process is in control. That's my certification. That's my story, and I'm sticking to it. Right? Why? Because I checked for all the rules. Everybody good? Now, one last point, which is look at this particular value. Here, I'm going to highlight this number. 62.10. Remember that number. And now tell me, what is your upper and lower limit for the X bar chart? What's my upper limit for the X bar chart? 65.88. What's my lower limit? 62.4. Is there a problem? So obviously I have this number 62.1 that's less than my lower control limit. Is there a problem? Why or why not?
Is it not a problem because it's within that particular sample?
That's exactly right. Remember what you're plotting. You are not plotting the actual observations themselves. You're only plotting the averages. So the averages are supposed to accommodate these outliers. The average is supposed to even out those outliers. That's why you're plotting the average. Remember what the goal of these charts is to understand systematic, not random variation. So you can have any number of outliers within your sample. That's fine. I'm just looking at the average performance during that hour. Okay? It's a good point, right? Which is called process capability. Capability says, now you measure yourself against what the customers want. Radical concept, right? What do customers want? And that's kind of the idea behind process capability, which is a more advanced kind of in the scheme of things that came later. Because people saw the major flaw here is that you could be measuring yourself against yourself in perpetuity and not make any improvements at all. And your customers could be different, markets could be different, technology could be different. You're not improving. So that's the next concept, which is process capability. So I'm going to create a new sheet here. Call it process capability. And I'm going to go back to my old sheet and call this process control, SPC. The notation for process capability is CPK. Don't ask me why that is. It's always been called CPK. Okay, it's like a kind of a manual definition or a reference book definition. CPK. That's your process symbol for process capability. So what's process capability? Let's define it. Process capability asks, where is your process mean? What's my process mean? Is it X bar or X double bar? X double bar. With respect to your customer requirements. Remember that plus minus 1? That's your customer requirements, not your control limits. In particular, process capability does not care about where your process limits are, upper and lower limits are, control limits. In this case, for example, customers have specified an upper tolerance limit. That is the tolerance versus control. Notice the difference in terminology. Upper tolerance limit of how much? How many ounces? It's plus or minus, so what's the upper limit? 65. And lower limit? Lower tolerance limit of? How much? 63. That's what customers are asking. Another term for this, by the way, different books have different names, or specification limit. It's called tolerance or specification limit, either one. Notice, either case, it's not control. Two different concepts. Everybody see? When you're drawing SPC, you're looking at upper control and lower control limits. When you're doing process capability, you're specifying, you're asking your customers to specify the upper tolerance limit and the lower tolerance limit, USL. And the notation for this, or the symbol for this is, you don't need to worry about that, UTL versus UCL for the control limits. Upper. So everybody good so far?
UTL?
Yeah, so let me specify that. Upper tolerance limit. And lower tolerance limit is LTL. Versus in the control charts, this is my UCL, LCL. This is my UCL of the range chart. And this is my LCL of the range chart. Okay, so now we are here. So now tell me, where is your process mean? What's your process mean? X bar bar is what number? What was the number? X bar bar? 64.15. 64.15, that's my X double bar. And so I'm going to go collect that. I'm going to say my X double bar is the 64.15 which I calculated. That's my X double bar. So, right? So the question is, capability is asking, where are you with respect to these upper and lower specification limits? It's not enough to be in the middle. Not enough. Let me tell you why. That's kind of the heart of CPK or process capability. This is telling you the fraction of time you're going to meet these limits. Because here in this case, I don't care what type of variation is happening. In control limits, in control charts, I don't care what random variation you have. All I care about is the systematic variation. But from the point of view of the customers, do they care what type of variation you have internally? They don't care. All they want is the 64 plus minus 1. So they don't care if you have random variation, systematic variation, all kinds of variation is the same for the customer. Customers are delayed, customers don't get the right product, customers have defects, customers don't get 64 ounces. That's all they care about. Everybody see? So CPK is measuring. So CPK is measuring what fraction of time you will be within your specifications. Limits is indirectly measured. I'll tell you how you can indirectly measure it. This is giving you your Z value. You guys remember your Z value? It's something similar to this. Okay, so let's look at this. In order to figure this out, you need to know what's the gap between the upper limit and the lower limit. But relative to what? Relative to your standard deviation. How many standard deviations? Standard deviation. So here's the formula for standard deviation. Given a sample, this is the formula. So we know our process mean. What is my process standard deviation? Process standard deviation is defined as R bar divided by small d2. So what was my R bar? Help me out. Go look at the table you had. What was my R bar? 2.39. I'm going to go collect it. This is my R bar. And what is my D2? Small d2. 2.059. That's just the formula. Why formula? Because in those days they didn't have Excel. These days, if you want to calculate standard deviation, how do you do it in Excel? You just take a whole bunch of data, collect the standard deviation. That's fine too, except it's not kosher. And if you ask a statistician, they will recommend you don't do the standard deviation across. You still do this R bar divided by D2, okay? Because we're dealing with a sample here, okay? But either way, do you get this value? 2.39 divided by 2.059, you get the standard deviation. So, and so what is a capable process? Now that you know your process mean and standard deviation, this is how you define a capable process. We define a capable process as one where the process mean, X double bar, is at least 3 times standard deviation away from both limits, UTL and LTL. So you want a 3 sigma gap. That's what you want. Everybody okay? Yes? Excuse me. That's how you define a capable process. So now help me calculate this. Are you within 3 standard deviations? So first let's calculate the upper gap, which is the UTL minus X double bar. What is the upper gap? What's the upper gap, folks? This is?
65 minus 64.
Which is 65 minus 64.15, which is 0.86. Okay? And what's my lower gap? X double bar minus LTL, which is how much? 64.15 minus 63. The question is, are you 3 standard deviations away? Is this number, what is 3 standard deviations? 3 times standard deviation. 3 sigma equals what? This is called the 3 sigma. What's 3 sigma here? 3 times 3.48. So you need to have a 3.48 gap between 3.48 gap between the upper tolerance limit and X double bar, and then between lower tolerance limit and X double bar. Do you have that here? Yes or no? What's the gap here, folks? Which number is greater? Is this greater or less than sigma or 3 sigma? Greater or less than 3 sigma? Yes or no? Is this greater or smaller? This is smaller. So does this satisfy the requirement at least 3 standard deviations away? No. This is less than 3 sigma. So this does not require, this not satisfy. So not capable. Even this is less than 3 sigma. Everybody see? Not capable. Sigma stands, of course, for standard deviation. Does everybody know that, right? Sigma stands for standard deviation. That's standard statistical terminology. If you want, you can also call this 3 standard deviation. But typically you call it, let me keep this 6 sigma because this is going to help me. All of you have heard of 6 sigma? This is the exact same concept of 6 sigma. Now you want a 6 sigma cushion instead of a 3 sigma cushion. Sorry? 3 times standard deviation. Okay? Yes? Everybody with me? So, everybody see why this is not capable? Because you do not have a 3 sigma cushion. You do not have 3 standard deviations cushion, which means what? That there's a good chance I'm going to spill over and I'm going to violate both limits because I don't have that 3 sigma. So to illustrate this point, what is the 3 sigma limit? Tell me for a z of 3, z value of 3, what is the probability of exceeding the upper limit? Z value of 3. You can actually calculate that as 1 minus norm S dist of 3, which gives you what? In percentage terms, 0.13 chance of exceeding the upper limit, and z equals minus 3. This is, again, it's going to be minus 3, and in fact you don't need to take 1 minus norm dist of minus 3. Again, it's point. So you sum it up, add up on either side, you get 0.13 plus 0.13 is 0.27%. So a capable process has no more than 0.27% defects. That's what a capable process is. That's why I said CPK is indirectly measuring what fraction of time you will be within your specified limits. And so in this case, it's not a capable process because it's less than 3 sigma. You don't have the 3 sigma cushion. The gap is less than 3 sigma. And so there's going to be a higher likelihood of violating these limits.